Hey everyone, welcome to the session talking about quantum-inspired algorithms as a mean of harnessing quantum advantage in NISQ era. So, like before going ahead with the session, I'd like to explain how the whole session will be structured. So there will be two components to the whole session. One would be the presentation deck, and the other would be the notes deck. The presentation deck would serve as you can say, major bullet points or the main points which I'll be covering in this whole, this session, and the notes would contain an in detail explanation of the main points which I talk about in the presentation. So the two things will go hand in hand, and I think both of them will be provided to you after the whole session, so you can go through both of them and use them as a as a contemporary material to each other. So without any further delay, let's get started. So here we have the presentation deck, and today, as I mentioned, that we'll be talking about quantum inspired algorithms as a mean of harnessing quantum advantage in NISQ era of quantum computing. So even before we get started with the whole presentation, it's important that I talk about what NISQ era is, because I'll be using this whole chronology of NISQ era a lot in this whole presentation. So basically, NISQ, as we call it, is noise intermediate scale quantum, or you would basically say, and phase of quantum computing, in which the computers which we have right now, the hardware which we have right now, are prone to error. They are not that much scalable, and they have their own limitations, as we'll talk about going ahead with the presentation. So yeah, so the first thing is, again, always is the introduction, in which I'll emphasize why even we are talking about quantum computing and what is the potential of quantum computing when we talk about solving large scale problems. Then I'll emphasize the limitations of quantum current hardware. In sense, I'll talk more in detail about NISQ era of quantum computing. Then we'll talk about some concepts of quantum mechanics that we particularly exploit when we are talking about quantum inspired algorithms. And yeah, I mean, let's I think before further delay, I'll switch to the notes part of the whole presentation, and we can get started. Yeah. So as mentioned, before we get started, it's important to talk about why even are we talking about this whole, why even are we having this session, to be very honest, right? So that would be the capacity of, yeah, give me a second. Yeah, that would be the capacity of the quantum computers to solve complex problems. So I think there already would have been a lot of sessions which will be particularly highlighting this aspect of quantum computing before you get to this session. But I'll try to keep it brief, just so that just for context, so that we have the continuity of explanation. So see, in quantum computing we have a concept called qubits, right? And just to put it in a very abstract sense, we know that the qubits, whenever we add one qubit to our, let's say we have, like, say, some n qubits here, like we have some n qubits which we are using to solve a problem. Let's say the problem is px, right? So if I'm adding one qubit to this whole system, I'm basically doubling my computing capacity, or I'm doubling the potential of the system to solve any kind of problem, right? That is how it goes. That is, I think that is what you must have heard by now, from previous presentations or by your own knowledge of this domain. So this is the core concept, right? This is one of the core concept of why we even want to go towards the quantum computing side. The problems, some problems, like you can say your traveling salesman problem, and then you have problems like you can say a topology optimization problem. You have your genetic, you can say your usual combinatorial optimization problem, I would say, combinatorial optimization problem. So these problems don't have a particular solution, right? So they work on approximate algorithms. So there's no better way to solve these problems rather than doing it on a quantum computer. So this, in some sense, is where we see the potential of quantum computers to be able to solve complex problems. But again, now this would be a sort of like a basic of why even do we go towards the quantum computing side. I mean, I think I didn't go much in depth for this particular section, and the reason for that being that I think it would be already being covered by other sessions, because I already saw the lineup. So they are like particular sessions which talk about exactly this aspect of quantum computing. Now I'll come to the more on the side of the things which actually makes sense, which is actually important in sense of what we are trying to achieve here. So that would be the limitations of current hardware. Let me switch to a different pen. Just give me a second. Yeah. See, the very first number, very first limitation is, how we put it, is scalability. So whenever we are talking about quantum computers, right, whenever we are talking about solving any kind of problems, so an aspect of scalability is one of the most important aspect. Because let's be honest here, right, whenever you're trying to solve an industrial case problem, the number of variables or the number of potential candidates, which you have to consider as a potential solution to a problem, they increase exponentially, right? Let's take a very simple example here, like, say I have to say, just basically find, solve this traveling salesman problem, but instead of a city, I have to solve it for a whole country, right? So it would make sense to you, right, that now the number of possible solutions, or the number of possible paths that the salesman can take, they increase exponentially, right? So whenever, basically we're adding one more point or one more possible end point or access point to the whole TSP problem, we are potentially increasing, we are doubling the number of possible candidates, right? So it's easy to see that, and scalability is an important aspect, whenever we are talking about any kind of problem. But that is one of the major limitation of current hardware, right? Because you can see, like, like there are multiple architectures which we have in, in our quantum computing domain right now. We have like annealing architecture. We'll talk about annealing in details later. We have gate based architecture. We have, your you have your topological qubits. Logical qubits. So these are some of the major architectures which we have in quantum computing. I mean all of them, they could be like superconducting qubits. You have your diamond head qubits, and your electron spin qubits. All of them are derivative of this major architecture. Here I'm talking about the architecture of hardware, not exactly the type of qubits which we use, right? So now, considering these architectures, they are, a certain hard limits or the number of qubits which we have available, right? And as we'll proceed, we'll also talk about, your quantum error correction as a sort of like a, what do you call, like an extra weightage which we need to carry, whenever we are trying to solve anything on a quantum computer, right? So coming back to this, so scalability becomes an important aspect, because see, due to certain aspects like quantum error correction, we are already losing some qubits. So say, by some chance, say, we had total n qubits available as given by any hardware vendor, hardware being the quantum hardware, and out of these capital N qubits, some, or say, some small n is usable, while some small m would have to be, reserved for certain aspects, as we'll talk in detail as we go ahead. Like there are aspects like, quantum error correction, ancilla qubits, support qubits. So those are not usable qubits. So we are saying that, even if we have this, capital N number of qubits, not every qubit, or every qubit is usable. That just means that, we are further reducing the scalability, and this value of capital N is already not that large. We are talking about 120 usable qubits, that is like more or less the upper limit which we have right now. And 120 possible qubits is not that much, as you have to take my word for it, because if I go in detail and try to explain, what different kind of algorithms would require different kind of number of qubits, then it comes out to be a large number. Any algorithm which you will develop right now on quantum hardware or quantum architecture will have certain limits, and those limits are very hard, and those limits do not scale well, when we are talking about scaling the whole problem into something which can be used directly in the industry, right? The second aspect, or let's say one of the second issues which we have in the whole quantum computing thing, is noisy qubits. Okay, so even if we say, we have, in the previously I mentioned that, say, we had n qubits, right? But I said that out of this n qubits, only small n are usable, right? But even the small n are not high quality qubits. They are not usually, so okay, when I say quality, so see, when I use a qubit, like any other, any other thing or any other particle, is just a, what do you call, like, say, if this whole box was my quantum system, then this qubit is a particle in that system, right? So in ideal situation, we would want this particle to be able to retain its property for largest amount of time, right? We would want this particle to be able to maintain its state, as we call it in the quantum realm, for the largest amount of time. But as as I'll talk about that, there are certain you can say losses which occurs, right? So this particle does not stay, doesn't is not able to maintain its state. So these what we call are known as noisy qubits, because over time, due to decoheration, decoheration, or interference, or through outside interference of material, these lose, they lose their potential state, right? So what would mean is that, say, like somehow, if I would like, if this was a quantum particle, this was a state of a qubit, like this has some information, which is important, right? But if I were to leave this qubit even in an isolated system, isolated system here being a quantum hardware or a quantum system, the state would be lost over time, and this would actually release back, come back to its original state, which is zero being your usual qubit 0 or 1. So this is usually called decoherence. And this what this leads to is that this leads to loss of information. So basically, you cannot rely on a qubit to be able to maintain its state. And other aspect to this whole noisy qubit thing is, one would be, as I mentioned, decoherence. The other is the error propagation. So what error propagation basically means is, like, I'll take an example of a gate-based architecture. So in gate-based architecture, what we usually have is, we have a qubit, which usually starts as 0, and it passes through gates, whatever gate is, X, Y, Z, Hadamard, or whatever gate it is, it passes through the gates. So yeah, for this talk, I'm assuming that you have the basic understanding of quantum computing. So that is something, which I sort of assumed in the beginning. So again, this would be the X gate, and then say, we have some different gates, say, Y gate, and then we had some different gates, say H gate. So every time a gate, a qubit passes through a gate, in mathematical sense, it's very easy for us to know, right? We, all of us at this point, if you have heard, read about basics of quantum computing, you already know, that every qubit is basically a matrix, right? So I'm having a simple matrix of 0 and 1. If this is basically for 1. So when I say I pass it through a gate, I basically means that I I multiply it with the matrix associated with that gate, in gate-based architecture at least, right? So we say we get some solution state, and which is the state at the end of this whole let's say all this whole circuit, right? But in actuality, in actual physical terms, in hardware term, we know that we use different possible principles, like we use microwaves, we use like certain what you call photonic radiations, right? And we use certain certain actual physical physical properties of these particles, to store the state of the particle, basically to change it, like to modulate it, right? So basically what we are saying is that after say, like if I started with psi 1, if I started with wait, just give me a second. Yeah, so if I started with psi 1 state, so what I'm saying that after passing it to every gate, I'm changing it to some state psi 2, and I'm changing it to same state psi 3, right, and so on. But in the course of this action, because I said that the qubits which we have right now are not of high quality, we lose we sort of lose some data, we lose some state of that particle. So some error gets propagated, like say some E1 error is propagated the first time we pass it through a gate, some E2 error is propagated the second time we pass it through a gate, and basically this goes on. So basically what happens is that now the E2 component will be a sum of E1 plus plus E2, basically the error of the previous gate plus the error of this gate. So what I'm trying to imply here is that there's a propagation of error as we go on to pass the qubit to gates. What this means, and what this actually means in terms of consequences sense, is that we have a limit to the number of gates or circuit depth, as we call it in quantum computing. So the circuit depth is limited. And limitation of the circuit depth would mean that you cannot apply certain algorithms, because certain algorithms require huge circuits, and those for for larger number of qubits, because see, usually we are, you will one thing which I think you got out of intuition is whenever we are talking about scalability aspect, we are basically talking about number of qubits. But it's also important to understand that when you increase the number of qubits, you are in some sense also increasing the circuit depth, because like more qubits require more gates, right? I mean, in sense of the circuit depth. So circuit depth and number of qubits both becomes an equal problem when you're talking about the scalability aspect of current hardware. And okay, then we have I'm talk about errors, right? So it's important to know that there are error correction code, quantum error correction code, or QEC as we call in short terms. But these error correcting codes right now are not of high quality. This is something of a very high research priority right now. There's a lot of research being done in this exact domain. So, but again, what does this mean in physical sense, right? So in physical sense, it means that even if we are able to get capital N usable qubits, we will only be able to use small n number of qubits, because we'll have to give this some m qubits for these quantum error correction codes. This m can sometimes be large. If you really want a good high fidelity results, right, then you'll have to make this m large, which would mean that this small n would be small. So basically you'll be limited by the number of usable qubits which you have for solving any kind of problem. So this becomes an issue. And again, one of the, you can say this is more on these were the major ones which have actually have physical implications. But there are like other smaller aspects as well, like you're talking about calibration issues, right? How do you calibrate calibration issues, like how do you calibrate these qubits? That becomes an issue. And then you're also talking about variability as a factor. Like the thing is that as I stated, right, in ideal world all the qubits should behave identically, right? But but in physical sense, it's important to understand that and qubit is basically a particle, right, that that follows certain principles. As you must have heard, just for context, that any qubit is any kind of particle that has two possible end states, which being 0 or 1. We are just naming it 0 1. It could be anything. It could be plus, it could be minus. As you must have heard so we have different bases, right? This is the computational basis. We have the planar basis, we have the polar basis. We have all, there are different kind of bases which we have. But any particle which has two possible end states, and as a possibility of being existing in a state, say psi, such that it could be a combination of both 0 plus beta 1, is basically a qubit. So qubit is in concept, it's not actually a physical thing, and physical particle can behave like a qubit. So that physical particle again will have its own limitations. But how do we ensure that all, say we have different particles, but all those particles behave exactly the same? Because, and say I can assure you that, okay, I tell you that, okay, this particle is a qubit, and I'll tell you, okay, this basically this P1 particle I tell you is a qubit, and this P2 particle also behaves like a qubit. But how do I make sure that these two are calibrated? They don't show any kind of variability, right? That again becomes sort of like an issue on the hardware side of things, to be honest. Like this doesn't have a lot of you can say limitation directly, but it becomes an issue when you're talking about from a more in-depth hardware perspective, right? So and again, and one of the other important issue which you'll face in when you talk about limitation is qubit connectivity. This is one of the issues which you won't directly have issues with. This won't become an issue to you, like if in the initial phases of your your planning your algorithm, but it becomes an issue later. So what happens is that, see, because we are, as I said, right, and every quantum hardware is basically a quantum system. So if I say that I had qubits now, so these I told you, right, every particle is basic a qubit is basically a particle that that follows certain principles. So say these are the particles, and I have already proved by some physics method or physical method that they have they fulfill the properties of a qubit. Okay, so now given that this system and this is a closed system, so this is a closed system. Now I already stated that this system is already in an acting quantum hardware, but the issue becomes here is that, see, there is a limitation of the connectivity between the qubits. Like say if say this is the kind of connectivity which we follow, and say this is connected to this and this is connected to this. So this is the kind of connectivity which you have. I think if you're interested in this, you can just Google connectivity graph of any, say quantum hardware, famous being the IBM's, or basically the IBM provides the quantum topography, or the, you can say, this particular connectivity map of all their hardware. So you can go look it up. So let's say this was some quantum hardware Q1. This is the connectivity map of that hardware. So now this is particle P1 and this is the particle P2. So these, or let's particle this is particle P3. So you can easily see that there is a direct path from P1 to P3. So now I'm trying to say run an 3 qubits algorithm. So I'm basically taking P1, P2 and P3, and all of them start with 0, because we initialize with 0. So it's easy to see that, okay, now say I have to make I have to use a CNOT gate, right, which is a 2 qubit gate, and I want to make the control qubit at P1 and basically the NOT gate at P2. So it's easy to see that it's okay. Let's make it P3 and this would be P2. Yeah, so it's easy to see here that if I want to perform this simple operation, it is possible, as my connectivity maps tells me that there is a direct connection between P1 and P3 particle, or P3 qubit, right? But what if I need to form a CNOT gate between P1 and P2, P1 and P2? It's easy to see that there is no direct path between the two. I'll have to connect, and there is a path. There's a path, but it goes to P3 and say P4 and P5 and P6 and so on, right? But there is no direct path. There is no one-step path from P1 and P2. So P1 and P2 are not directly connected. This becomes a limitation. Okay, there are ways to do it, right? It's just, if I didn't tell you, so this is not. Even if I want to do this operation, it's not a wrong operation. It is possible. We have, we basically use swap gates now. So what basically a swap gate is, just for context, is, in simple notation term, we just represent it through 2 x's. This is basically a swap gate, but in actuality, a SWOT swap gate is basically 3 CNOT gates. So it's like this, and this. So you can basically the swap gate has a whole matrix associated with it, and if you multiply the matrices for 3 CNOT gate, or tensor product them, you also get the same matrix. So basically you can usually in theory we just use this notation, but in hardware sense this is what happens in the background. So now what this swap actually means is now if I want to go from P1 to P2, I'll basically be swapping this P3 with P4 and swapping this P4 with this P5 and P5 with P6 and so on, until I'm able to swap P2 with P3. So basically I'll swap this gate with this, right? So it's easy to say here that what I'm saying right now is that for every swap, I'm basically adding 3 CNOT gates, and every CNOT gate is basically 2 single qubit gates, right? One is control and one is CNOT, one is the NOT gate. So basically what I'm saying is for every step I'm having 6 gates more to the circuit. So for this kind of operation, let's say which we had 1, 2, 3, 4, 5, 6, 7, 8. So it's basically 8 into 6, like 48 gates just to do a single operation. Single logical operation, but 48 physical operations needed to be done in order to do that, right? So it's easy to see that this affects the whole scalability aspect of our hardware. So again, qubit connectivity becomes an issue, when you're talking about, the broader sense, the limitation of NISQ era devices. So these were some of the major limitations of, you can say your NISQ era devices, and why even we are considering, these are some factors why we do not basically run all the algorithms which we have right now on quantum hardware. Like, these are the things which are stopping us. These are major research points. I'll be honest with you. This is not I'll not say that this is something which will affect us for a longer time. Like, people are diligently working on these things, particularly to improve the state of the current hardware. But this is what I say, what I mean when I say that we are in sort of like a NISQ era of quantum computing, where we are limited by the current hardware. So just last put it, so this I talked about NISQ. So now I think every point, every single wording of this whole abbreviation should make sense to you, right? NISQ, noisy. We talked about noisy qubit. Intermediate, because like we are in an intermediate stage right now. Scale, because the scalability is a very huge issue right now. We do not have scalable hardware. quantum, because again we are talking about quantum hardware, so why not? So this NISQ should make sense to you. I spend a lot of time on this because it's important that you understand what are the limitations, why are we even talking about this, why are we having this session, why are we even talking about quantum inspired algorithms when we already have algorithms for quantum hardware. So now comes coming to the main subject, quantum inspired algorithms. Quantum inspired algorithms. Okay, so what are quantum inspired algorithms? So let's go with the wording first. We have quantum, again, which would mean quantum mechanics principles. Inspired, meaning that we are inspired by the principles. We are not exactly able to, we are not able to simulate them in some sense. But sorry, we are not able to, we don't have that hardware of that kind. We are not doing it on exactly on a quantum mechanics realm, right? But we are simulating those properties. So inspired would mean that we are simulating those properties. Simulating. And algorithms, again, is a series of steps. So basically, when we say quantum inspired algorithms, we are talking about the algorithms which simulate some quantum mechanics principle to get performance benefit. I mean, it wouldn't make sense, right? If you don't get any kind of a performance benefit. So we are talking about some performance benefits that go along with the algorithm. So coming back to the presentation now. So again, we talked about, in the introduction, we talked about, the potential of quantum computers to solve complex problems. We talked about NISQ era, basically the whole NISQ thing, and we introduced the concepts. Now we'll go in detail in the whole concept thing. Again, this is something which we have already covered, basically understanding the NISQ era of quantum computing. It's important to understand the challenges and, the limitations which we face with the current hardware. And again, we could now talk about, you can say, basically the third point, which means leveraging the use of quantum inspired algorithms to still get some advantage, but not exactly be limited by, the hardware of current time. As you will see that basically when we talk about quantum inspired algorithms, which we are basically saying, as I stated, that we are simulating the properties of quantum computer. We are simulating some quantum mechanics principles. Those principles I'll talk about in the next few seconds. So those simulating certain properties of quantum computing to get benefit. Right. So this simulation happens on classical hardware, and by a lot of work done by our ancestors, classical hardware is at its very best right now. In some sense, we do have great hardware. We have GPUs, we have CPUs, we have GPU CPU collaborations, right? So we have hardware that is classical hardware that can scale. Again, one thing which I would like to particularly point out, in no sense by simulating the property of quantum mechanics will we be able to get the whole benefit, or the full potential. We won't be able to achieve the full potential that these algorithms have. These algorithms are basically, in the end, are meant to run on quantum hardware, but because the hardware is still in the budding stage, we are just simulating them on a classical hardware and still getting some performance benefit. So basically the thing of essence here is that scalability is possible on classical hardware. Even if we are not exactly it's like you can sort of say like a sort of a trade-off. On a real quantum hardware, we expect huge performance bonus, but scalability is an issue. But in quantum inspired, the trade-off is that performance might not be that big as compared to the pure quantum hardware, but the scalability is there. We are potentially able to scale them in order to solve you can say industrial problems. So that is where the essence of quantum inspired comes into play. Okay, so again we have talked about what quantum inspired algorithms are. I sort of talked about the motivation, why even are we considering quantum inspired. We are considering quantum inspired for its scalability aspect and still being able to deliver some performance benefit, because again we are here because it's some kind of performance benefit is what actually a performance boost is actually what we are behind. So again let's come now. I'll talk about the properties. I've always been saying that we use certain properties of quantum mechanics and this and that. What exact properties am I talking about? The very first is parallelism, or as I like to call it, parallelism or superposition. superposition. So even before getting in whole in exact detailed discussion of his concept, I'll take a very simple example. So let's say I have a coin, right? And for any coin we have two possible end states, heads and tails. Now let's say that this is a qubit. For the sake of this discussion, I'll assume that say this my coin is a qubit. Now whenever I flip this coin, right, and I say that it falls into my wrist, right, it falls into my wrist, and now I close my wrist. So until I open my wrist, there is a 50%, I mean this heads and tails, there's a 50% chance that it could be heads, and there's a 50% chance that it could either be tails, right? So we can say this particular coin right now is in a parallel position. It is a parallelism, is in a state of parallelism, it's in a state of superposition. It's equally likely to be heads, it's equally likely to be tails. Or if for the sake of this consideration, as I have previously mentioned, that I'm considering this qubit is this coin is basically a qubit, and we know that I talked in very slight details that any qubit basically should follow this principle, that it should be able to should have a state which should be defined in with the help of this alpha and beta component, which I think you guys should know that this the square of this alpha and the square of this beta is basically the probability of this particular state psi after measurement to either gives heads or to either give tails, right? So this is some basic understanding which I sort as I previously mentioned, I'm sort of assuming that you guys have this kind of understanding. If you don't, don't worry, you can just record this, you can just pause this session and you can go back and just type an introduction to quantum computing. You might even find my some of my videos back there. But yeah, my point here being that, say, okay, now the sake of this, coming back to this discussion, for the sake of discussion, as I said, I'm assuming that the coin is a sort of like a qubit. So in theory it should follow this principle as well, right? It should also have this coin should also have a state, right? And as a state, and as I previously mentioned, that a coin has two possible end states, heads or tails. So basically the state of a coin should be, we should be able to define it in this sense as alpha heads plus beta tails, where the square of alpha and the square of beta defines the probability of the coin being either heads or tails respectively. So because for the as I previously in our case, I'm seeing that the coin is in my fist, right, and my fist is closed. So by common sense we can say the value of this alpha and this beta, the square of these values, are both 0.5, right? Because as I said, right now it's in a 50-50 state, right? So it's 0.5, right? Square, the value of the square is 0.5, the actual value would be somewhere around 1 by under root 2, right? Because 1 by under root 2, the square would be 1 by 2, which would be 0.5. So basically alpha and beta, if to be precise, would be 1 by under root 2, and the square of these values is 1 by 2 or 0.5 or 50%, right? This is what we call superposition. Now how exactly does this come into play in actual you can say quantum computing aspect? So what happens is that, see, okay, now there were only two possible states, but now in some sense I'm saying that there's one single coin C1 which has a state psi1. When it is in the wrist, right, it is a combination of heads and tails, or basically it is a combination of two states existing simultaneously until we open the wrist. So just for context, the opening fist basically is what we call measurement, which again is a again is a concept which you must have heard when you were studying introduction to quantum computing. So basically measurement is at the end, measurement is nothing but after I open my wrist, it should always be either heads and tails. It cannot, now after I open my wrist, it cannot be in that in between state, right? Now it has to be decide, now it has to either be heads or it has to either be tails. So that definite at end, that finite, that discrete state which the state which the quantum particle has to fall into, this is in some sense called measurement. Measurement in actuality is a bit complex, or it's a complex concept, but if I talk about it, then I'll also talk about a computational basis, and then I'll talk about how exactly it's like the best example I can give of measurement is like, you're just talking this cat, the whole experiment. Until you open the box, the cat is both dead and alive, right? But as you open it, as you observe the particle, you observe the cat, it has to either be dead or be alive. Then it cannot be in a state in between, right? Exactly like a coin, as soon as you open my wrist, as soon as I observe my coin, now it has to be either heads or it has to be tails. Exactly, in actual theories, in qubit, which has two possible states like 0 or 1, as soon as I perform the measurement or I observe that particle, it has to be either 1 or 0. Now it cannot be in that in between state. But in quantum computing, what we do is we take benefit of the principle or the possibility of this particle to exist in state of in between say 0 and 1. We take the advantage of this, while it's still in superposition. And what we do is, like, see, this I'm talking about in pure quantum computing sense right now. So what we do is, we modulate these values of alphas and betas. And by doing that, we are basically modulating the final result which we will get when we perform measurement on this state. So let's, for the sake of convenience, like very simple example, if we had a black box and we need to find the solution, this black box is basically a function fx, and we need to find the minima of this black box, or minima of this function, right? And for the sake of this convenience, let's say that the minima was 0. Right, the value of x being 0 is what gives the minimum value of this function fx. I mean, the sake of this convenience, and we are using only one qubit. Say 0. So this right now is in a state where alpha is 1 and beta is 0. Right. I mean, I should just make it 1. I think for it would be better. So it would be alpha is 0 and beta is 1. Right, for the particle, I mean, because following basically this whole aspect. So now that we know this, now we know that the solution, I mean, in our case, for the sake of its convenience, we know that at the end the alpha should become 1 and beta should become 0 for the particle after measurement to give this discrete value 0. Right. Now as an algorithm designer, instead of in this case we know what we need to do, but usually we have a fitness function which tells it how close we are to a solution. We have some function, let's say we have some finite function which tells it how close we are to the solution. Okay, so, or some methodology by which we keep telling the algorithm that okay, you are approaching to the solution, you are getting farther from the solution, so make changes accordingly. So let's say that here, because we already know and we are an observer, so we know we need to at the end make this alpha to be 1. So now what I'll do is I'll make an algorithm which the particle after let's say I'm using an Hadamard gate. After I put it into a superposition, I'll now perform certain operation which will make sure that after those operations, this alpha becomes 1 and beta becomes 0. In this case, because we had one qubit, so there was no sense of using parallelism. But now let's say we had n qubits. So now when we are talking about using n qubits, we are basically talking about 2 to 3 n potential states existing simultaneously. When the n was 1, basically we had 2 states existing simultaneously, right, which was 0 and 1. So we would basically checking the values of 0 and 1 both for the black box, right? And we saw after, because now in this case, so we already know, like we just saw that okay, this has to be 0, so we make alpha 1. So but in our, let's just say we did not know that. So now in some sense, we are basically using the 2 values simultaneously for checking the value of the black box. This is exactly what happens in Dutch algorithm or Dutch-Zoska algorithm if you're taking multiple qubits, and for single qubit it's called Dutch algorithm. So you can look it up. I mean, it's a pure quantum algorithm. It's Dutch algorithm. Okay, so this was, this is once in some sense what superposition is. So superposition is basically using 2 to the power n possible states simultaneously for a given function fx to find whether which of them is the closer to the solution or which of them is the solution sometimes. So that would be even the Grover search algorithm takes advantage of this, which is comparatively a bit popular algorithm. So that also takes advantage of quantum superposition. Again, now this principle is, we can say, one of the most important principle which we make use in quantum inspired algorithms. So if you talk about, I'm talking from a very simulation sense here. what we are basically doing is we are changing this alpha and beta parameters, right? For any particular you can say particle, we are just state, or say we have the particle psi1. These are a function of these two particles, alpha and beta. So if we modulate this alpha and beta, we are, in some sense, we can simulate this quantum property, right? So initially, what this mean is that initially put it something random, and over time keep on modulating the property to alphas and betas, and according to the closer you reach to the solution state. So this is, in some sense, how we simulate quantum parallelism in quantum-inspired algorithms. And this is some sort of like an important concept. And again, the second concept, which we usually have in quantum-inspired realm. Let me just change my color. Yeah, quantum tunneling. This is more if quantum superposition was more on the gentle concept, quantum tunneling is more prone focused towards your quantum annealing concepts. Your quantum annealing is basically, as I previously mentioned, is a type of architecture which we use. We'll talk about. So annealing, I think annealing in general, I think you do have an idea, right? Annealing is basically like over time, like if you heat a metal, over time it cools down, right? So every particle in this whole universe has a tendency to be in a minimum state of energy. So if I draw the the energy versus time graph, if I draw this, so every particle will eventually reach that state of global minima, or global minimum energy, right? That's a property. So they will basically utilize this property to what we call simulate and to basically find the global minima of certain functions, right? Fx. So basically, when I say fx, it doesn't mean that this is only limited to your function optimization. In theory, it's said that any kind of problem which you're trying to solve, if it is always possible to map that problem onto a function. And so every problem in the end just becomes an optimization problem, if you think about it, right? So this fx is basically the problem which we are trying to solve. Okay, now let's say the landscape of this function fx over x is, say, along this line. It's along, it changes like this, right? So as I said, annealing works on a simple concept, classical annealing I'm talking about. It will keep going down, right? It will keep going down until it reaches this point. Let's just give me a second. Okay, this was how it was, but you can see that this is a local minima, and this right here is the global minima, right? Now here is a limitation of classical annealing. Now if it needs to reach this global minima, it also needs to go over this whole steep hill, right, until it reaches this valley, right, and of this whole you can say landscape, right? But here whereas classical would be would depend on randomness, or would depend on a sort of like a miracle, right, to just cross this whole throw. And in quantum we have a concept of tunneling. Okay, what exactly is tunneling? I'll give you a brief about it. So what happens is that, okay, this is, interestingly enough, quantum tunneling was discovered while we were trying to improve a classical hardware. So what happens is that, okay, in as per Moore's law, you already know that the number of transistors which we have on an integrated circuit doubles every decade. No, every 3 to 4 years, right? So that means that if you're doubling the number of transistors, that would be, there are two ways of doing it, right? Make the IC chip larger, or make the transistor smaller, right? So again, it's obviously not possible to make the IC larger, because we want our devices to be smaller, not bigger, right? So we make our transistors smaller. So see, again, there's a limit to which we can reduce the size of a transistor. After a certain limit, the quantum mechanics principles comes into play, and they start interfering with our results, and we don't get the idealistic results. So when that happens, people, the scientists started to notice that there is this phenomenon which happens of quantum tunneling, that the transistors become so small that electron just passes through them, and they don't have to interact with them, they just pass through them. So this is what they call tunneling. So in our respect, what happens is that in quantum annealing, there's a possibility that we can just the quantum particle, the particle which we have in annealing, they can just tunnel through this whole this whole steep and directly reach this point. And then by usual annealing, we will be able to find the global minimum. This is sort of like the concept of quantum tunneling, and this is the concept which we used when we talk about quantum inspired annealing. Quantum inspired annealing algorithms, which I think you do have a session on again. So again, I won't go in bit of detail about this, but this is another concept of important concept which we use when talking about when designing, you would say, quantum annealing algorithms. Okay, so these are these were the two major one. We do have concepts of quantum entanglement, but those are sort of like pure quantum concepts. And there is no, like, it's very hard, or it's close to impossible to sort of get those on simulate them on classical hardware. So these are very advantageous if you have quantum hardware, but in quantum inspired world, it becomes a bit harder to simulate these, so we don't particularly rely on these things. Okay, so these were some of the basic basic or important principles of quantum mechanics, which we try to simulate whenever we are trying to work on or designing quantum inspired algorithms. So we just cover this slide. Yeah. So this the previous slide I talked about the principles which we usually employ when we are talking about designing quantum inspired algorithms. So this slide talks about some of the major, you can say, quantum inspired algorithm which we do have in operation. So it also, surprisingly enough, not many people know this, but algorithms like QAOA, or quantum approximate optimization algorithm, you have variational quantum eigensolver, and even your quantum neural networks, you can say, all of them are in some sense example of your quantum inspired algorithms. So how that come into play is that, see, what happens usually is that these algorithms have basically what they do is like they map the problem. We have a problem statement and they map the problem onto a function, right? And what they try to do is they try to optimize that function, and while optimizing that function, as I previously mentioned, they try to use the principle of quantum parallelism to improve the result. Again, these algorithms, as I like to call them, are also quantum ready. That would mean that you can run these algorithms on actual quantum hardware as well. So what they basically you can say assure you, or they try to guarantee you, is that in future when you will have better hardware, you should be able to just take these algorithms from here and just put it on a real quantum hardware and get all the benefits of quantum computers as well. And okay, now now I'll talk a bit in detail about some of the use cases which we have of these quantum computing, quantum inspired algorithms. And one of my personal favorite being quantum inspired optimization algorithm, which is sort of like my specialty, sort of like what I particularly work on. Yeah. So okay, so again, some of the, let me just switch my color. Some algorithms. So one of the most famous and common algorithms are your QIO algorithms, quantum inspired optimization, as I call it, basically optimization algorithms. Again, which is something which is more of my expertise. This is where my expertise lies. So in QIO we have evolutionary algorithms. We have annealing algorithms. So these would be the two type of algorithm which we usually have in quantum inspired optimization. In evolutionary algorithm, you can have a number of algorithm like QGA, quantum inspired genetic algorithm, basically quantum inspired particle sum optimization, quantum inspired Wolf optimization algorithm. In annealing, you'll have your usual annealing algorithms. So I'll not go in detail about each and every algorithm, but I'll try to give you a glimpse of how they function. So basically, any kind of optimization problem is basically optimizing a given function, and this fx is basically the mapping of a problem px. So every function has a landscape. Let's say this was the landscape of this function, and within this landscape there is one global minima, right? There could be multiple local minima. This is also local minima, this is a local minima, this is a local minima, this is a local minimum. I'm talking about this is like a 3D projection just viewed from above, but in actual sense you can also look at it like this. Say this could also be the landscape, and you can see here that this should be the global minima. So now what happens is that when we are talking about your classical optimization algorithm, so they usually follow a very first I'll start with simple gradient based algorithm like your stochastic gradient based algorithm or gradient based algorithm. They start with some point x. So this is this is some point x. So these algorithms then follow this gradient of the landscape. So in our case, it's easy to see that this algorithm is likely to get stuck in this local minima, because it won't be possible for the gradient based algorithm to make the jump to this side, right? We also have stochastic based algorithms which can make this jump, but again they too have the limitation, and for a complex, say non-convex what do you call landscapes, they fail. So that is where evolutionary algorithms come into play. Evolutionary algorithm, see, I'm talking about classical evolutionary algorithm right now. So those do solve these problems. That is why so if you ever worked with genetic algorithm, then you must have heard it that genetic algorithm can, in theory, solve any kind of problem. Given that, first thing is you can map that problem into onto a fitness function fx, and second is that you have infinite computational resources. Those are very computationally expensive, your genetic algorithm and stuff. So how the genetic algorithm or any evolutionary algorithm in general works is that they prepare candidates C1, C2, C3, C4, and they prepare candidates, and they test every candidate on this function fx, right? So this candidates would basically mean maybe some random points on the landscape, some random points on the landscape. So they depend on the theory that out of all these candidates, one would perform the best. In our case, this is the best performing one, right? Let's name it C3. So C3 is now the best, and the worst is, say, in our case, it's obvious to see that, okay, this was C1, then C1 was the worst performing. Then C1 would get eliminated. It just follows the basic Darwinian theory of evolution, that fittest of the, the survival of the fittest, right? So C3 is the best, C1 is the worst. Now we perform certain operation depending on what kind of evolutionary algorithm we are working with. So in order to ensure that more candidates in the next generation are towards C3, right? So basically, we keep on repeating this process until we finally reach this point x, right, or our global minimum. This is how your evolutionary algorithm works, right? So where does quantum come into play is this, that, see, as I said, that the biggest bottleneck here is the computational resources for genetic algorithms or for evolutionary algorithms. So if you remember, I talked about the principle of quantum superposition. So what that would mean is that now I can test multiple possible. Okay, so for any precise state, we know that there are two possible parameters, alpha and beta. So if I modulate this alpha and beta by using some, I won't go in details, but by using some operations, then I should be able to check multiple multiple candidates on this landscape simultaneously in single operation. So basically, I use this advantage of quantum superposition or quantum inspired superposition to improve or to reduce the number of generations it would take me to converge, or basically I would improve the convergence rate, and I would reduce the computational resources required, because I'm actually saying that even if I use less number of candidates, say small n, then also I am assuring that I can still converge to the global minima. So that is in some sense how we look at quantum inspired algorithms from a practical point of view. We are talking about scalability, right, and still getting some performance boost over the classical hardware, and that is one of the reasons why we are even going towards these kind of algorithms. So I personally, just for the context, I have worked on QGA, quantum genetic algorithm, that is QPSO, quantum inspired sampling algorithm, quantum inspired sampling algorithms. I have worked on like some of other quantum annealing algorithms and everything. So okay, just for quantum annealing, we use the same concept, but because in annealing we are talking about reducing the minimum state of energy, so we convert our function fx into a Hamiltonian. What is a Hamiltonian? You can look it up. Hamiltonian is basically an energy function which we try to minimize. So some of the practical use cases which I have myself worked on by using this evolutionary algorithm are some of the one of the huge industrial use cases. There would be airfoil optimization, there would be topology optimization, and much more. So these are some of the problems which I have personally worked on, and if you look it up, so these are very industrial and very high scalability problems. They are computationally very expensive. The function fx associated with this function fx associated with both of them, it is very expensive. It's not easy to evaluate this fx multiple times continuously. So it's important, it becomes very important. The less the number of times I need to calculate this fx, the better my algorithm is. So I was able to I was able to get best results and better results for these two kinds of problems. So these are sort of like the use cases which I have worked on. There are a tremendous number of use cases. So as I previously said, right, that every problem px which takes argument as x can be you can map it onto a function fx, then you basically need to perform function optimization over this function, right? You just need to improve the fitness or improve the value of this fx function, so it becomes a function optimization problem. So basically any combinatorial optimization problem can be mapped to function fx, which can be solved using quantum inspired optimization algorithms. So that is, in some sense, I'm talking about it from a very abstract blueprint point of view. That is in some sense how we use quantum inspired algorithms to perform certain industrial or practical applications. So again, this is what I particularly highlighted in the given, you can say, given notes, that what are the benefits of quantum inspired algorithms, that they perform certain, give you certain performance boost over your classical algorithms or classical counterparts, while still being able to maintain in some sense scalability, right? But again, there are some limitations of quantum inspired as well, because see, as I stated, that we are not using the full potential of your quantum computers, right? We are still sort of simulating the properties. So whenever we talk about simulating the properties, it's important to know that we are restricting the performance which we can get. So this restriction, depending, that in some sense, in actuality, depends on you. How much performance can you give up for scalability, and how much performance do you actually need? To be honest, in the problems which I mentioned, like the airfoil problem, the topology problem, even a slight performance benefit or a slight performance boost means a lot, because it's such a sensitive industry, and the function which which I'm trying to optimize is so computationally expensive that even if I'm able to reduce it by 10 generations, the convergence rate, that means a lot. So that totally depends on the kind of problem or the kind of use case you are targeting. Okay, so as I talked, considering all of this into perspective, taking this into perspective, it's easy to see that quantum inspired algorithms provide an immediate solution of harnessing the advantages of quantum computers, or the principles of quantum mechanics, and yet not being directly dependent on the hardware side, the limitations of hardware. So they do provide you a sort of like a key opportunity to dive deep into the whole quantum computing aspect in sense of practicality and sense of application basis, and yet not being directly dependent on your hardware limitations. So but this again is sort of like what you call like a backup plan, or something like an immediate plan of action until eventually we get the hardware of high quality, which is where we actually run our quantum algorithms and get the so-called quantum advantage, as we call it, also the quantum supremacy, as we like to. We don't use this term anymore, so I might get some backlash from using the term quantum supremacy, but in some sense I'm talking about the pure quantum advantage. That is something which we can only do after we have proper quantum hardware. But for the time being and until that happens, quantum inspired algorithms are a good way of still harnessing the advantages of quantum mechanics principle by simulating them on a quantum hardware and getting you can say some kind of performance benefits for your use cases or your applications. So yeah, this is sort of like the whole the whole session. I had to keep it a bit short and did not dive deep in depth with a lot of concepts. So in the future, I might as well do different sessions on that, or if you're interested, you can reach out to me in person, and you can ask me any questions which you have, in-depth question or detailed question, or if you want to have a conversation about detailed discussion about some of the concepts or some of the use cases or applications which I pointed out but could not discuss in detail because of the shortage of time and everything. So I'm always welcome. Is always welcome from my side. You can always reach out to me. So that was pretty much it for the whole session, I hope you learned something new. I hope, because I think one of the problems which I used to face, I'm used to hearing, is that, I mean, from a commercial and industrial point of view, is that if the if this is not scalable, if it is not that scalable, why are we even going with it? Why are we up put because investing a time with this whole thing? Well, my answer to that is quantum inspired algorithms. Is like the immediate answer. Like, I'm still using the principles of quantum mechanics, I'm still using my knowledge of quantum mechanics and quantum computing and quantum information, but I'm simulating those in some sense on classical hardware. So I'm still able to get some advantage and still able to maintain some scalability. So quantum inspired is sort of like one of my favorite things, because I get to enjoy quantum computing and yet I don't have to worry too much about scalability. It is a bit complex. It does get a bit complex because sometimes that trade-off, you have to decide on that trade-off, and it does not always good, and it's not always about rainbows, right? You have some limitations to this quantum inspired aspect as well. But overall, I mean, as I said, that it's one of the potential perfect methodologies of harnessing the advantages of quantum computing in this era. So yeah, I mean, that would be it. And I mean, thank you for your time and patience. And again, as I stated, that I'll add another slide after this and the deck which I'll share with you guys, that which will contain my contact info, so that you can reach out to me, and you can ask any questions you have. And if you want any detailed if you want to get a conversation about detailed discussion of any of the topics, I'm always here. And feel free to reach out to me. So thank you.